Hi all, Chris Weishaupt here. Today I'm going to talk about an electrical leakage failure in a medical endoscope, how we were able to determine the root cause of the electrical leakage, the tools we have at our disposal for determining what types of chemicals devices were exposed to, and the component level tests we can use to design for better device chemical compatibility and reliability. The device that originally detected the electrical leakage was a Fluke ULT 800 electrical leakage test kit. This is a test kit used at hospital facilities to verify that the device is intact and that it does not pose an electrical shock risk to the patient. Our goal with this analysis is to determine where the electricity is leaking in the probe, why it's leaking. There's lots of potential various pathways, either through the materials that make up the probe or through an electrical short from like a hole or a delamination between two of the materials. Corrective actions as far as handling the probe, what the hospital can be doing better, and what we can do better on the design side to make the probe more reliable. There are many potential tools we could use to go about solving this problem. In this case, we're going to focus on the Fluke ULT 800 electrical leakage test kit, infrared spectroscopy, and electrometry, measurement of volume and surface resistivity. When using the Fluke ULT 800, one test lead gets plugged into the back of the endoscope, and the other test lead sits in a water bath. In normal usage, you immerse all of the patient contact surfaces in the water bath. The Fluke ULT 800 generates 120 volts AC and measures the current leakage through the endoscope into the water bath and to that other test lead. The pass criteria here are that the current leakage must be less than 185 microamps. This other check here that the current is greater than 20 microamps is basically just a check to make sure that you didn't forget to plug in one of the test leads. By isolating various sections of the probe, we can eliminate some of these electrical leakage pathways and figure out where the problem actually is. So for instance here, we've immersed only the tip of the endoscope and we passed the electrical leakage test at that point. So that allows us to eliminate all of these materials and interfaces as potential leakage pathways. By eliminating the articulation sleeve, these roving joints, the tip material, the acoustic window, we basically leave only this polymer sheath of the insertion tube and potential holes as the electrical leakage pathway. One important thing to note here is that we couldn't find any localized leak in the sheath. Like we could immerse the bottom end of the sheath and cause a failure, or the top end of the sheath and cause a failure, and we couldn't find any small localized region of electrical leakage. So this suggests that there's a systemic problem with that insertion tube. Here I've cross-sectioned an endoscope to give us an idea of the construction and the electrical leakage pathway. Endoscopes are typically constructed of this inner metal coil and a wire braid. These are both typically connected to a common terminal. The ULT 800 applies 60 volts AC between that common terminal and the probe that was in that water bath. So you have 60 volts across this material here. In all of our testing, we were not able to discover any highly localized electrical leakage. It seemed like it's a systemic problem across the entire endoscope sheath. Our visual inspection similarly did not find any holes or tears or delaminated interfaces. So this suggests that the actual conductivity of the material has increased, or the resistance has decreased. We have to answer then, why do we think that happened? Is it contamination? Is it increased water in the material from humidity or soaking in water too long? And so to do that, we need to turn to another instrument. We're going to turn to Fourier Transform Infrared Spectroscopy, or FTIR, to determine the chemical composition of that endoscope sheath polymer and see if we can find any contaminants present in the material. In infrared spectroscopy, we see peaks that correspond to various molecular structures and functional groups in chemicals and polymers, and that allows us to determine the composition. In our case, we're using ATR, or Attenuated Total Reflection sampling mode, which is nice because you don't have to do much sample prep. You just press your sample up against, in our case, a diamond crystal using this anvil mechanism. Here's a diagram of an attenuated total reflection, or ATR crystal. The infrared beam comes through the crystal, bounces back and forth by total internal reflection. There's a small evanescent wave that extends into the sample roughly by this equation here. So we end up with a depth of penetration that's dependent on the wavelength. So we're sampling a little bit deeper on this side and a little bit shallower on this side, but roughly a micron or so of penetration into the sample surface. And that's where we're actually measuring the chemical composition. Here I've made this video to kind of show how the resonant frequencies of the various vibrational modes correlate to the observed peak structures. Carbon dioxide, or CO2, is a very simple molecule. It only has two asymmetric vibrational modes. We have this vibrational mode here that generates a peak at about 2350 in the middle of the spectrum here. Now that's the asymmetric stretching, and then we have the bending mode that generates a peak at about 667 centimeters to the -1. Centimeters to the -1 is a way of saying wave numbers. Wave numbers is just a convenient way for us to present the x-axis in IR analyses. We could present it as wavelength in microns, but it ends up looking better if we put it in wave numbers. Wave numbers is how many wavelengths of light fit into 1 centimeter, thus the centimeters to the -1. Here I've shown the infrared absorption spectrum for the failed device in red, and for that same endoscope sheath material on a reference device in blue. We can see some peak structures that are typical of polyether urethanes. We have the ether group CO stretching here. We have carbonyl from the urethane linkage here at 1700-ish. We have NH stretching and OH stretching, so all very typical things of a polyurethane. But if we look very closely, we can see that there are a few additional peak structures present in the failed specimen in this area, and these peaks are the most easy to observe. This suggests that there may be some kind of contamination present. If we take that failed specimen and subtract the spectrum from the reference specimen, we generate this spectrum here shown in gold. This spectrum shows a very broad OH stretch and a strong carbonyl peak with peak positions consistent with some type of carboxylic acid. We can then run that spectrum against our FTIR library database and find reference compounds that match that spectrum. In our case, the most closely matching compound is 2-furoic acid, which is indeed a carboxylic acid. 2-furoic acid happens to be the primary ingredient in the Revital-Ox Resert Disinfectant that was used to disinfect the endoscope. It makes a lot of sense that having an acid in our polymer would make it more conductive. Those ions make the material more conductive. We found that after soaking the endoscope in water for 24 hours, the acid diffused out of the endoscope. We were no longer able to detect it by FTIR, and we then passed the electrical leakage test. And then just as a sanity check here, we have our subtraction result, the 2-furoic acid library match, and here we've taken some of this Steris brand Revital-Ox Resert Disinfectant and dried it down and showed it here, and we see, yes, the peak structures are very similar. Key takeaways at this point are that it's important to follow the recommended disinfectant usage time. If you exceed that time, you're increasing the likelihood that material is going to diffuse into the endoscope and cause problems. Equally important is to follow the manufacturer recommendations for rinsing the endoscope after disinfection. If they say rinse for 5 minutes or 10 minutes, you have to do that because that rinse is important for extracting any chemicals that have diffused into the endoscope. Also, you can avoid any uncertainty in these stages by using an automatic disinfecting station. The last takeaway here is that we have tools for detecting residual contaminants and seeing what sort of chemicals devices were exposed to in the field. On the reliability and design side, we need to be thinking about how quickly does this disinfectant diffuse into the endoscope? Is it going to be okay after a typical 8-minute disinfection? Is our rinse time adequate to get this material out of the endoscope? And then from the design stage, are there better materials we could be using that are less susceptible to diffusion of this chemical? And what kind of test could we use to answer that question? Can we do it at the component level and not have to make a $10,000 plus device each time we want to run a test? On that last subject, yes, we do have ways of validating and optimizing our materials at the component level so that we don't have to invest in an entire device each time we want to run a test. So in our case, we might look at something like ASTM D543 or D471 for mass swell and extractables in various disinfectants. Now that's typically an equilibrium swell and equilibrium extraction test after several days, so that won't tell you how quickly anything's happening unless you take measurements at several time points. And here we've done that for this Revital-Ox Resert and that sheath material, and we find that after about 4 hours, it's equilibrated at about 10% mass swell. We could then try other materials and see if it equilibrates at percentages lower than that 10%, and maybe those materials could be a better option for us. If you want to look at how quickly diffusion is happening without doing these multiple time points in a mass swell study, you can do something like this Franz diffusion cell. I've done this before where you take a membrane of your polymer material, put it on the Franz diffusion cell, add your donor compound to the top, clamp this together, and then you periodically sample from DI water that's underneath here and measure the concentration of whatever analyte you're trying to measure diffuse. This concentration in the bottom typically starts at 0, so given Fickian diffusion for small times, this is typically a linear rate here, showing the diffusion of whatever analyte you're concerned with. And then obviously there are a ton of other standardized tests we can use depending on what you need, depending on if adhesion is a concern, if abrasion is a concern, if tensile properties or tear properties are potentially important, if the density is important, like for ultrasound materials. And then we have other options, of course, like FTIR, GCMS, LCMS, biocompatibility, and cytotoxicity to see if the chemical composition of our materials has changed after disinfectant exposure. Here our focus is mostly on electrical properties, so we're going to jump into ASTM D257 measurement of volume resistivity of our materials after disinfectant exposure. ASTM D257 describes test methods for measuring the volume resistivity on tubes and sheaths. You can then use the measured volume resistivity rho, the thickness of the material in question, and the surface area of the material in question to calculate the expected leakage current for your material. You can measure that resistivity after 8 minutes of disinfection, after rinsing, after prolonged soaks in disinfectant, and to determine which materials are going to be best and which disinfectants are potentially going to be problematic for you. Running ASTM D257 requires some specific instrumentation. In our case, we're using a Keysight B2987A electrometer, which is capable of delivering up to 1000 volts DC using its internal power supply. The method calls for 500 volts, so we're able to do double that. You also need to be able to measure very small currents. This electrometer can measure electrical currents as small as, I believe the rated resolution is 0.01 femtoamps. A femtoamp is 10 to the minus 15 amps, so that's something like 62 electrons per second is the resolution spec on this electrometer. You also need to be able to log the electrical resistance over at least 60 seconds of that applied 500 volts. In order to do that, we're issuing commands via SCPI instrument commands through MATLAB, having the instrument log the data, and then at the end of the test, MATLAB asks for the data from the instrument. It gets sent over the network, and MATLAB does all of our plotting for us. In this case, we used a thin sheet of the endoscope sheath material and measured the volume resistivity before and after an hour in our Revital-Ox Resert Disinfectant. We found that the volume resistivity decreased by 2 orders of magnitude after that 1 hour in disinfectant. That's 100 times increase in the amount of leakage current. So now we have a standardized test for component level electrical properties that we can use as we see fit. We can do a 1 hour exposure like I showed on the previous slide. We can do a standard 8-minute disinfectant usage, measure the electrical resistance, then do a rinse, see if the electrical resistance changes at all. Or we can do a worst case scenario, which is let the material sit in the disinfectant for several days until it's gone to equilibrium, and that'll give us an idea of what are the worst disinfectants. In the worst case scenario, somebody forgot the probe in the disinfectant over the weekend. What are the worst disinfectants that we need to worry about? And in this case, we found that Revital-Ox Resert, Super Sanicloth, bleach, transeptic were some of the worst materials as far as diffusion and changing the electrical properties of the material. It's not maybe realistic, but the worst case scenario is useful, both for seeing which disinfectants could be problematic and for comparing various materials. If we had another material that showed only 1 or 2 orders of magnitude drop in electrical leakage in that worst case scenario, maybe we should consider switching to that material. In summary, we were able to isolate the electrical leakage to the endoscope sheath material. We found that the sheath material was contaminated with acids from the disinfectant. We found that if we rinsed the endoscope in water, we were able to extract those acids and the electrical properties recovered. We were then able to pass the electrical leakage test. And when we tried to expose the endoscope to disinfectant to reproduce the failure, we found that it took about an hour for us to fail the electrical leakage test. And then most importantly, we developed a range of component level testing options that allow us to examine our different candidate materials and our different disinfectants and evaluate if something's going to be a problem before we have to go about building a $10,000 plus device. I hope this presentation gave you an understanding of a couple of the tools we can use to assess field returns. We can assess the root causes of any observed customer complaints or product failures, and most importantly, we can work on component level material validation tests to help us optimize the materials we're using and understand the reliability of our device and the susceptibility to various chemical exposures.